Most machine learning models hand you a single number and act completely certain about it, even when they've never seen data anywhere near the input you asked about. That confidence is often an illusion, and it can be dangerous. Today, we're looking at a model that does the opposite. A Gaussian process gives you a prediction and, right alongside it, an honest measure of how sure it actually is. Let's unpack how that works and why it's so elegant. To appreciate what makes a Gaussian process special, let's put it next to the kind of model you probably know already. Ordinary models output what we call a point estimate. You feed in an input, and you get back one value, full stop. The trouble is that the model looks equally confident whether the input sits right in the middle of your training data or way out in territory it has never seen. It cannot tell you when it's essentially guessing. A Gaussian process reframes the whole problem. Instead of committing to a single curve, it defines a probability distribution over functions, and it considers every function that's consistent with your data at once. So at any input, it returns a mean prediction and a spread. Tight where you have data, wide where you don't. The uncertainty is built in, not bolted on. So how does it actually turn a handful of observed points into a curve with uncertainty attached? Let's walk the pipeline. Everything starts with the kernel, also called the covariance function. This is where you encode your assumptions about smoothness. The kernel decides how strongly two nearby inputs should have correlated outputs, which is really just a formal way of saying similar inputs tend to give similar answers. Next, you condition on the data. You take your observed points and pin the distribution to pass through them. Because everything here is Gaussian, this step has a clean, exact solution. There's no iterative training loop grinding away, just a bit of linear algebra. Out of that conditioning comes a posterior, another distribution over functions, but now shaped by what you've seen. This posterior is the updated belief about which curves are plausible after the data has spoken, and it's still fully Gaussian at every point. Finally, you read it off. At any input you care about, the posterior gives you a mean, which is your prediction, and a variance, which is your uncertainty. Near your data, the variance shrinks toward zero. Far away it grows, honestly telling you the model is extrapolating. Now that we've seen the mechanics, let's pull out the three ideas that really define a Gaussian process. First, it's a distribution over functions, and the kernel is what shapes it. Choose a smooth kernel and you get smooth curves. Choose a rougher one and you allow wilder behavior. Your prior beliefs go straight into that choice. Second, calibrated uncertainty everywhere. This is the headline feature. The model doesn't just guess. It tells you how much to trust each guess, which makes it a natural fit whenever data is scarce and knowing your confidence genuinely matters, like robotics or Bayesian optimization. Third, it is what we call non-parametric, meaning it grows with your data rather than fixing a set number of weights in advance. That flexibility is wonderful, but there's a catch. The cost scales cubically with the number of points, so classic versions struggle once you pass tens of thousands of observations. Let's gather the essentials into 4 takeaways you can carry with you. A Gaussian process defines a distribution over functions rather than fitting one fixed curve, averaging over all the functions your data supports. Its real superpower is calibrated uncertainty. Every prediction arrives with a spread that's tight near your data and wide where the model is extrapolating. A kernel encodes your smoothness assumptions, and because the math stays Gaussian, conditioning on data gives a clean, closed-form posterior with no training loop. Because it grows with the data, it is flexible but cubically expensive, which is why it shines on small, precious data sets. If ideas like this one click for you, Standarity.com has a growing library of plain language AI explainers waiting.